Hello everybody and welcome to our webinar Safety Analysis in ICEM Surf. My name is Honorata Frinks and I will moderate this webinar today for you, while Nick McFerrin, who's preparing his screen right now, will explain you the safety analysis functions in ICEM Surf. This webinar will be recorded and you can rewatch it on our Cartier Creative Design community later or as a webinar on demand on 3ds.com. And of course, you will receive the direct link to the stream tomorrow in the afternoon or evening, wherever you are right now and which time zone. At the end of this webinar, you can ask questions and we will have some information on future webinars and events for you, so stay tuned. And if you have any questions in between, please write them into the question window. We will collect them and answer them afterwards. And now I hand over to Nick. Have fun.
Hello everybody and welcome to this presentation of safety analysis on ICEM Surf 2018. Today we're going to have a little bit of a talk about it, and I'm going to take you through an overview of the functions of the safety analysis, including classic head impact and our advanced features for 2 and 3 touching sphere analysis and tornado lines. Okay, then we'll keep a question and answer session for the end. I'm going to try to do live demos for you this afternoon, so I hope you enjoy them. So ICEM Surf, as you know, has been around for a while, and the most recent releases have included major enhancements to safety analysis. So if you weren't aware, I hope you'll find them very interesting and useful. So for safety analysis, it's an optional module to ICEM Surf. It's called K77. Okay, you can see it here on my screen. And here we go. So to activate your license, you go to the Windows licensing menu, and you can activate it here in the licensing K77 with just a tick. And then when you're in ICEM Surf, it's under the diagnosis menu under check safety analysis. Okay, so classic head impact analysis. What is it exactly? So in the past, it was very important to make sure that there were no sharp edges on the vehicle that could injure a passenger or a pedestrian. So what they used to do is they would do a rolling ball analysis where they would take a sphere and cover it in paint, and they would roll it around the interior of a physical model. And where the paint touched the model, they would then analyze the radiuses, the sharp edges that the ball could touch. Now, obviously, this took a very long time, and you had to make the physical model, and it was just a very tricky thing to do. So what we offered our customers was the ability to do this digitally before a physical prototype had to be made. So it's the perfect opportunity to check for your certification for those minimum radiuses. So for instance, minimum radius might be 2.5 millimeters or 3.2 millimeters. These are standard values for head impact analysis. What we're saying here is these are the smallest radiuses permitted in case you had a head impact situation. Okay, so the way that it works is you look at the picture over on the right here, there's the rolling ball representing the head form, typically 82.5 millimeter radius. That's a standard size. And you can see the colors on the screen on the picture. The green, so the blue areas are where the ball just cannot touch. Okay, so it doesn't bother analyzing the radiuses of the blue areas. The green areas show the ball can touch, but it checks the radius and it determines that the radius is comfortably above the 3.2 specified minimum in this example. But you can also see there's a red area on this image. This shows that the ball can touch the surface, and when it checks the radius, it falls below the minimum radius allowed. Okay, so this isn't going to make your model safer, but it's going to give you the information that you need to check what the minimum radius situation is. So I'm going to go through some live demos. So let's get my ICEM Surf. Okay, where is it? Excuse me. Sorry about that, just a second. Great, okay. So here we have a grill. just a simple grill. Okay, so I'm going to start my head impact analysis, my safety analysis. Diagnosis, check, safety, there it is. Okay, so what we have to do is pick the surfaces we're interested in, all of these, thank you very much. My radius is 82.5, and I'm going to check for a minimum radius of 2.5 millimeters. I'm going to use a manual mode. We found this is typically the best mode for the first pass, and we can choose a tolerance or an accuracy. So this is based on tessellation. So this is a little loose, I'll be honest with you, but for the demonstration, I want it to be fast. But typically you might use a finer tessellation than 0.05. You can also specify length. What this means is that this is a maximum edge length for the tessellation for the vectors. So I'm not going to use that right now. I'm just going to go with this one. So let's see what we get. It takes a moment or two to run the analysis. I'll switch off shading. There we go. All right. So what do we have here? So we can see blue, green, and red. And we also have these little stars. The green arrow, by the way, is pointing in the direction the ball is coming from. That's quite important. All right. That's what the normal orientation option is for. Okay. So taking a closer look here, we can see we've got these little asterisks marking. These are the worst places. The reason why we added these little hints are because we can also use an edge mode, and sometimes you can miss where the worst areas are. So these are just markers to make sure that they're easy to find. We have a vertex mode as well. I don't like this one very much. I prefer edge or shading. Okay. We can also switch on labels. Okay, so if it wasn't obvious enough, it says below curvature. And we can also activate the sharp bend with topology. So this just shows the edge. But as this is Y0, it doesn't really make any sense here. All right. So that's basic head impact analysis, but there's some other features here on the screen. We have the inspect function. This is a reassuring tool. What we can do is this allows us to pick on a surface, and that puts a representation of the head form directly on there for us. Okay, so the sphere is green here, so I can then go inspect and pick, for example, a red area, and we get a red sphere. This gives us the confidence to pick directly on problem areas and to get that feedback that we need. Okay. Now we have a couple of extra things here, additional safety radii. What's this all about? Well, what this allows us to do, let me just switch that off. Okay. I'm going to show you individual first. So individual allows us to specify, like it sounds, an individual surface for the analysis. So I'm just going to pick this fillet on the top here. Okay. Now you can see the value I've specified here is 10 millimeters. Let me just, there we go, that's what I wanted. Okay, so most of the model is being analyzed with a radius of 2.5, but just these two surfaces are being analyzed at 10, all right? And you can see that it's failing the analysis right here. But an interesting feature is also at this point, we can click on the 10 and we can change this. So I can make this 5 and it'll rerun the analysis immediately. Well, let's make this one 50, see what happens. Okay, so it's very flexible and very, very intuitive and easy to use here. So the other option I wanted to show you was separation. So I'm going to change my list. What separation does, it allows you to specify a zone, a separate zone with a different set of numbers to use. Okay, so I have a surface here that's sort of slicing through the middle. So I'm going to say this is my separation surface. I'm going to select it. Okay, so we get another arrow. So this is pointing towards the zone of separation. So what this means is in the direction of the arrow, in this case beneath the surface, we're going to check for a minimum radius of 30. Okay, I appreciate it's a little large, but just to make a point, I thought I'd show it to you. So take a look at this green marker here. I'm going to rerun the analysis. Let's see what we get. All right. So what you see here is there's these red areas on the side. They're actually appearing under here. You can see the markers are placed on here for us as well. And if I flip the normal on the separation surface, if I made a mistake and got it the wrong way around, you'll see the opposite happens. The red will appear in the middle. This is typical for perhaps in the interior of a vehicle. You might have a knee zone where the regulations specify a different minimum radius to a head impact area, for example. Okay, so I'm going to jump back to the presentation. If I find it, there we are. Oops. So we're going to move into touching sphere. So this was a new feature that came in at 2017, and it gave us 4 new options for a touching sphere simulation. 2 regions, 2-region lift, 3 regions, and a 3-region lift. What this means is it was simulating or providing us with where would a sphere would touch 2 zones, and you could specify a point, and it would give you the depth that the sphere invaded or stepped down below. It's a little hard to explain. It's better to show you in a live demo, which I will do in a moment. And 2-region lift is comparing 2 balls or 2 spheres with a lift value. And the 3 lift is a similar arrangement. But I'm going to show you on a live demo because it's a little easier to understand that way. All right. So going back to our grill here, I'm going to restart my diagnostics, and I'm going to choose contact sphere. So we'll start with a 2-region. Okay. Now, actually, what I want to do is reset that. I don't want to see this. Oops. Okay. So 2 regions. So I'm going to pick a fillet on the top here. Let's say this one. So with the touching sphere, you need to be a little more precise with your selection. And I'm now going to pick these ones down here, or this one here. Okay. Now I can pick a position at this point, and I can pick a place here on the surface and say, okay. Now we have some options. So here's the sphere. Okay. Switch that off. So you can see it's giving us a depth. There's quite a lot on the screen, so we can actually choose what we see. So that's what it's done. It's put the sphere across these 2 fillets, and it's generated this depth value. All right. So this is very important for your certification. These are the information that you need to feed back to make sure that you've correctly analyzed your minimum radii on this situation. Okay, and the nice feature here is we can save this information out. So we can save these lines and the sphere to be geometry if we want. Okay, so we can rerun it again and pick different positions, but here's a little tip. If we do that, right, so I'm going to pick the same surfaces again. Now, without picking a position, I'm just going to go straight for OK. And what happens here, the system has given me 500 measurements all the way along both sets of fillets. This is a little bit more useful. And also notice it gives us a minimum and a maximum depth. Okay, so this is, to do this manually would be extraordinarily difficult, but here a count of 500, that's a little high to be honest. Let's make that 100. There we go. And that's fantastic. Okay, so just to give you a little clue as to what's going on here, I just want to show you something. Here's a little tip. If I make a fillet, radius 82.5, an arc fillet, I can then make it between the same surfaces. Here and here. There we go. So that is effectively the fillet that is being made by the analysis automatically. Oops. Okay. So then what we could do is we could extract these tan lines and we could use them for building geometry or for marking on the model where we wanted to be concerned with. Okay, I'll delete those. All right, let's take a look at the lift function. So what happens with the two-region lift? You can see in the icon here, it's giving us a clue. This is an important part of safety analysis to check the lift, or I would consider it a drop, between the center of two spheres in this situation. Okay, so I'll set up the analysis and let's see what we get. Now we get asked for a reference edge, so I'm going to pick a reference edge. Whoops. Sorry. There we go. On the top. There, that's what I wanted. And let's do the analysis. Or did I not finish that selection? Okay, I'll do that again. So from here to here, referencing this edge on the top. There we go. Now, what this number represents here is the H value on the icon. Okay, so there's a rolling sphere like before running between these two fillets in this direction. Okay, but then using the reference edge, there's a second sphere rolling across the top. And what these values represent, this is the H value, it is the distance between the centers of the two spheres. Okay, so this is very important for the certification. So you can pick any reference edge around the model, but this one I picked just for clarity. So this is the H value. Okay, I'm going to move on to 3 regions. So it's very similar as you might expect. So I'm going to use the same fillets. And this time I'm going to add these ones over on the side. All right, if I put the sphere on, you'll see what's happened. So the system has automatically calculated for us the 3 touching points on the fillets. And it's given us these values between those touching points. And if I put off the sphere as well, it also has generated the depth for us. How far in does the sphere penetrate the model? This sort of thing would be very tricky to calculate manually, take a long time. And it would be, it would be very tricky. So this is a huge time saving for checking the minimum radiuses of your model. Moving on then to 3-region lift. So similar to 2-region lift, as you might expect. Okay, I think if I just pick a reference edge. Oh, and this little one too. Okay, I thought I might remember my selection, but no. All right, so let's do that again. All right, there we go. And if I put the spheres on, hopefully you can see what's going on here. So this is, for example, like a secondary impact situation. So if the first impact is the blue sphere and the second is the orange, and it's dropped down into the grill area. If I switch off the spheres, you can see what's going on. So ICEM Surf has automatically generated for us the same contact points as before, but also it's given us the sideways motion from the centers of the spheres, and also the depth, the drop down, or the lift, as we call it. Again, we can save these for future reference. Also notice we can have a variant. So we can save different sets of numbers and different choices, different options into different variants to save time when you come back to redo your work on maybe a different project. Okay, so let's go back to PowerPoint, and we can take a look at the tornado line. So this came out with 2018, so this is brand new. People say, what is a tornado line? Well, it's this bone line that you see on a lot of cars these days, these sharp feature lines that are appearing on the exterior of the cars. Sometimes they look very sharp indeed. Using modern production methods, they can be quite sharp. So it's important that they're safe. And there certainly are lots of regulations about what is safe and what isn't. So the European regulations are associated with the ICER 21 and ICER 26. And in the US, they have the equivalent of these numbers here, FMVSS 201. I'm sure you can read the numbers just as well as I. So what is actually going on here? So it's a little complicated, but I'll try to explain. Taking the 82.5 radius sphere, because it's the standard measure we like to use, we're pushing it on the inside of the tornado shape. So this V shape you see, this is the tornado, the feature line, and on the inside we're pushing the sphere. Okay, and what the tornado analysis is going to give us is the H value. Okay, the H value is the distance between when the sphere is touching on the top and the bottom points. It's the value between, it's the shortest distance between the sphere and the extent of the fillet that's on this feature on the tornado line. So this H value is very important because here we are. It has been defined that the radius of a fillet on a tornado line must be bigger than, well, the radius must be equal to greater than H divided by 10. So sorry. So the folds in body panels may have a radius of curvature of less than 2.5 millimeters, provided that it is not less than 1/10 of the value H of the projection. So to put it simply, if H is 25 millimeters, the radius must be greater than or equal to 2.5 millimeters. Okay, so again, it works better if I just show you in a live demo how it works. All right, so here we have an example. Let me get rid of that. I tell you what. All right, so we'll go back to diagnostics, check safety, and we'll go for the tornado this time. So what we do, first of all, we pick our first set of surfaces, which I'm going to go across the top here. Our second set is below the fillet. You can see there's not much of a tornado in this example, but let me show you how it works. Okay, that's the second set, and the reference is going to be the fillet. Okay, so I can just pick that in one go. There we are. Okay, so I'm going to start the analysis, and this is what we get. Now, it's a little bit small, so I'm going to change the scaling. All right. So remember, this is the H value. All right, so it's not telling us if our fillet is safe or not. What it's saying here is, so taking the maximum value, it's about 1 millimeter, 0.956, okay? So if you remember, if we divide that by 10, that is the minimum radius allowed for the fillet here. Now, if we take a look at the fillet, we can all see that it's comfortably above that. We can just check that on this front one, for example. All right. change my U and V direction. So there you go. So it's 16 to 18. So that's absolutely fine, as you might expect. But it's not a very sharp feature. This is safety analysis after all, and this isn't going to create any problems at all. So I've created another little example just to reiterate the point. So I've constructed this shape. It's a little bit sharper. And let's see how this one behaves. So we choose the tornado. So my first surface is this one. Second one is that one. And the fillet is my reference. All right. Oh, I need to change the scale this time. This is a different situation. So you can see that it's a much sharper piece of geometry here. So let's take that down to 1. Okay, there we go. So what does this mean? The numbers are 15.3 and 15.089. So this means that the minimum radius allowable here, according to the regulations, it's about 1.5. All right, so what we can do is we can then check the curvature of this surface. And it's a different UV. There we go. All right, so I've got it set to minimum radius with 2 colors, and we're getting this red line across the model, and we can see it's 1.4. All right, so this is telling me that this radius is far too tight for this sort of tornado line, so this would fail the regulations. It would have to be changed. All right. So I hope that's clear. Okay. So there we go, back to the presentation. Here we are. So that's actually, I finished going over the technical parts of safety analysis. I hope you're getting your questions ready. But while that's happening, I just wanted to draw your attention to some special events coming up. Here we are. So we got the Dassault System User Conference 2018 in Hanau in Germany. It's a multi-brand event, and it will be very interesting. There's going to be Simulia and CATIA present. And also coming up very soon is we have an interesting webinar for the CATIA Creative Design Business Process Flow. So if you can, we'll give you this link at the end, but you can register for that webinar as well. And also for ICEM Surf students, ICEM Surf is currently free until October 31st. So again, if you want to come back to us at the end, we can tell you how, if you know any students who would like to download the free version, how they can get their hands on it. Okay, so I'm happy to open the webinar to questions.
If you have any questions, just write them into the question window or raise a hand.
It's a very technical subject, so it takes a little bit of processing to think about it.
But I think we're good. So if there are no more questions, I'd like to thank you for your attention. You will get this recording of the webinar tomorrow. And I hope to see you in the next webinar. Have a lovely afternoon, evening, or morning, wherever you are. Goodbye.
Goodbye. Thank you.